Hello, everyone. This is So Yang from the University of Minnesota. Today, I'm going to introduce our speaker, my friend and colleague, Professor Peng Zhao. So, Professor Peng Zhao is an assistant professor of mechanical engineering at Auckland University. He obtained his PhD from Department of Mechanical and Aerospace Engineering at Princeton University in 2015, advised by Professor C.K. Luo. His research interests primarily focus on fundamental-based and application-oriented problems in the frontiers of combustion, propulsion, fuels, and safety. His current research activities include open-source multi-physics modeling, low-volume, high-throughput output, fuel ignition screening, advanced engine combustion strategy, Li-ion battery safety, and thermal runaway, etc. He has published nearly 40 journal articles and one book chapter, which I would say is very amazing for anyone at his stage. With a Google Edge index of 15, he was awarded the Bernard Lewis Fellowship by Combustion Institute in 2018, and he's a member of the Early Career and Diversity Development Committee of the U.S. section of the Combustion Institute. So I always consider Peng as a rising star in our field and also a role model. In spring 2021, I think this is his good news for us. He will join the University of Tennessee, Knoxville as an associate professor in the Space Institute and the Department of Mechanical Aerospace and Biomedical Engineering. So Peng will move and also promote it. That's very good. And I think because of this Space Institute, he will add more research towards aerospace direction. So let's see what Peng have for us today.
Okay, thank you very much, Dr. Yang, for the kind introduction. And dear colleagues and friends, it's really a great pleasure for me to introduce you my recent research on hotspot flame initiation, as well as lithium-ion battery thermal runaway. In the beginning, I want to give a brief introduction saying why this problem is important and what are the fundamental concepts I want to briefly review. Basically, in power cycles and propulsion systems, combustion frequently needs to be triggered at the desired timing of each cycle. So such active combustion control is frequently realized using the spark plug or the laser ignition system. So during this process, you will have the ignition energy stored in the ignition coil or the laser pulse to be deposited locally in a short duration of time, and leading to subsequent thermal and chemical change in the mixture. And in other cases, due to the heat transfer with a wall or imperfect mixing, pre-ignition knock may occur due to the ignition from hotspot. So a very simple way to model this class of phenomena is through the problem of hotspot ignition, where a hotspot is characterized by the heat deposition by imposing a heat source term or a temperature profile, initial temperature profile. Although the complexities such as the electromagnetic waves and shock waves and plasma ionization sometimes are ignored, but the crucial fundamental processes, including the transient energy deposition, heat mass transfer, detailed chemistry transport, and flame stretch are accounted for. On the other hand, as reviewed by the lecture from Professor Igofopoulos a couple of weeks ago, by serving hundreds of recent combustion literatures, he has found that the majority of the laboratory flame experiment is conducted under ambient or only slightly elevated temperatures. However, in a practical system such as piston engine, gas turbines, scramjet engine, you have the unburned mixture being compressed by either the piston motion, flame dynamics, or the compressor, or a sequence of shock waves, such that there's a substantial mismatch in the thermodynamic conditions in the inlet mixture or the unburned mixture. So that will lead to the gaps in understanding of flame dynamics and chemistry, and that will lead to the missing novel physics and combustion features. So that's why I want to talk about the flame initiation problems under the elevated temperature conditions. So before I continue, I want to review two major important concepts for the hotspot ignition problem. The first one is minimum ignition energy, which measures the critical ignition energy needed to successfully trigger a self-sustained flame. So the left-hand side shows experimental data on the unbuilt-in area. You can see that when the ignition energy is low, the flame kernel basically cannot be initiated. With gradually increasing ignition energy, you can say we can successfully initiate a flame. And the right-hand side is a simulation on the hydrogen-oxygen mixtures. Basically show the same thing. There exists a critical ignition energy above which you can successfully trigger a flame. So there are many analytical solutions and even scaling laws on the minimum ignition energy in the textbook and literatures. The second concept that is relevant is on the flame propagation regime. So basically, as shown in the experimental data on the lean undecking air mixture in a spherical combustion bomb, you can see that on the both of the flame speed versus radius and flame speed versus stretch rate plot, there exists three different regimes. The first regime is being driven by the ignition energy, followed by a unsteady regime, regime 2, and eventually leads to regime 3, which is a stretch flame dynamics regime. And this regime 3 contains the data that we would like to have to either do linear or nonlinear interpolations to obtain the flame speed. The right-hand side shows the simulation results. So basically, you can say that as shown in the black curve, the trend and regimes as shown in the experiment are successfully captured. However, if you decrease the ignition energy, instead of having 3 different regimes as shown in the experiment, sometimes you can have 4 regimes as shown in a bump of the velocity at point C here. And this regime 3 is basically called an overdriven flame, which occurs when the ignition energy is close to the ignition energy, or for mixtures with larger than 1, with Lewis number greater than 1. Okay. So depending on the ignition energy and the mixture, there can be either 3 or 4 flame regimes during the flame initiation propagation process. So with these 2 fundamental concepts in mind, I'm going to show the outline of today's talk. The first story I'm going to talk about is the cool flame direct initiation. The focus is on the minimum ignition energy and flame regimes, as well as the stretch dependence of cool flames. The second is we focus on the recently observed negative temperature dependence of iso-octane flame speed under high temperatures as measured in a shock tube at Stanford. And by performing one-steady simulations, we can explain that negative temperature dependence using by observing a thermal pyrolysis induced overdriven flame. In the third part, I'm going to show how I extended the hotspot ignition phenomena and the concepts to the study of thermal runaway ignition regime of lithium-ion batteries. So the first part, cool flame direct initiation. So the simulation is performed using an open source reacting flow platform based on OpenFOAM. And the mixture we select, the fuel we select is dimethyl ether, one of the simplest fuel, including the low temperature kinetics. Under ambient temperature 300 Kelvin and 1 atm, the flame initiation process is largely similar to the hydrogen case we have just shown. You have either a successful initiation of a hot flame or you have an ignition failure. However, when we increase the ambient temperature from 300 Kelvin to 600 Kelvin, although we can still have hot flame at a very large ignition energy and ignition failure at low ignition energy. And in between, there is a range of ignition energy, which gives you cool flame, which with a much milder flame radius, the evolution rate. So the cool flame is fundamentally the coupling of low temperature chemistry and transport process. So as shown in the thermochemical structure comparison of a cool and hot flame, you can see that the cool flame has a much lower flame temperature, and also the cool flame will have different combustion products. Instead of lots of CO2, it has a long tail of formaldehyde in the downstream. And the cool flames has been recently reviewed by Professor Zhao in his 2 review papers, and one is in a topic review in a symposium. So if we trace the minimum ignition energy needed to initiate a cool flame, we can find that the cool flame can only be initiated in this low to intermediate temperature peninsula, and the cool flame can be initiated with a much lower ignition energy compared with a hot flame for the same mixture. And also cool flame can be initiated with a much wider equivalence ratio range. This is consistent with the extended flammability limits of cool flames as identified by Liang and Law using the turning point of premixed flame. So with this R versus T plot, we can easily obtain the evolution of the cool flame speed in terms of flame radius, cool flame speed in terms of stretch rate. So as shown in this plot, similar to the hot flames, the cool flame evolution also shows 4 regimes: ignition-driven regime, a transition regime, an overdriven regime, and a stretch flame dynamics regime. Although with the similar similarities in the flame initiation regimes, there is a substantial difference on the cool and hot flame response to stretch. So following the classical theory of stretched flames, the flame stretch induced by flow non-uniformity and flame curvature will couple with a non-equal diffusion of heat and chemical species, basically manifested as non-unity LE number. And this coupled effects of flame stretch and Lewis number can affect the burning intensity of the flame. As in the case of a positively stretched spherical expanding flame, you can have super adiabatic flames for the Lewis number less than 1 mixtures, for example, lean hydrogen or rich hydrocarbon flames. As shown in the experimental data, as you can see that the rich undecking air mixtures tends to burn weaker with a decreasing stretch rate, while the lean undecking air mixtures tends to burn stronger with the decreasing stretch rate. And the consistent trend is observed for the dimethyl air mixture hot flame, where under the lean conditions and rich conditions show the same trend, which is also consistent with the stretch flame theory. However, if you look at the evolution of a stretched cool flame, the behavior is very different. So the cool flame tends to always burn slightly stronger with reduced stretch rate as the flame expands, regardless of the mixture equivalence ratio is lean, stoichiometric, or rich, therefore regardless the Lewis number of the mixture. And such a phenomena, of course, it cannot be described by the classical stretch flame theory. And the reason for such a behavior is because the low temperature chemical equilibrium is gradually shifted as your stretch rate changes. As the flame expands, your stretch rate gradually decreases, which allows a longer residence time within the flame structure. So the cool flame, the low temperature chemistry tends to be more complete, and adding a little bit more heat, the temperature is also higher. So this shifted quasi-equilibrium of low temperature chemistry can explain such a behavior of the cool flame dependence to stretch. So the first part, the take-home message is we have performed unsteady simulations at elevated temperatures, and we found that cool flame can be directly initiated in a low to intermediate temperature peninsula, and a cool flame can be directly initiated in a much wider range of sequence ratios. And also the cool flame initiation exhibits similar flow regime as a regular hot flame. However, the cool flames tends to always burn stronger with reduced stretch rate, regardless of the mixture sequence ratio. So that's our understanding from the first work. More details can be found in our recent symposium paper. And the second part of my talk is we try to focus on the negative temperature dependence of the iso-octane flame speed as recently measured in a shock tube. And we try to understand what causes such a behavior. And basically, I would consider one of the major advances in flame experiment is a high temperature flame speed measurement in a shock tube as conducted in Professor Hansen's group at Stanford. So we all know that a shock tube can give you a well-defined time zero and a nearly constant elevated pressure and temperature conditions followed by the reflective shock. So what they did is they have added a laser ignition system in the test section of the shock tube, which triggers a short laser pulse followed the reflective shock wave. And they use a high-speed camera with a band pass filter to capture the chemiluminescence of OH radicals on the flame front. And basically, they can sample different points along the circumference of the flame, and they can do the data processing largely similar to those in the conventional spherical combustion bombs, and they can do the linear, nonlinear turbulations, and the results on the simple fuels like methane and propane have good consistency with the experimental data, with other experimental data, and also with the kinetic modeling data. So what is more interesting is actually for the flame speed of large hydrocarbon fuels, the iso-octane flame speed. And what they have found is there is a non-monotonicity in terms of the temperature dependence of iso-octane flame speed. As you can see here, that this average burning velocity is basically the average the flame speed for the radius range from 0.7 centimeter to 1.7 centimeter. And what they have shown is that the average burning velocity gradually increases, monotonically increases with temperature in this low temperature range. And same thing, gradually the monotonically increases in a high temperature range. However, in the intermediate temperature range around 750 kelvins, they have found a negative temperature dependence. Well, one direct conjecture might be, okay, this is similar to the NTC effect in the ignition ignition process, where the ignition delay shows the NTC behavior. But however, if you compare with the ignition timing versus the flame measurement time, you can find that the ignition delay, even in the first stage ignition delay, is at least 2 orders of magnitude shorter, 2 orders of magnitude higher compared with the flame measurement time. What it means is that during the flame propagation time, the unburned mixture is hardly affected by any auto-ignition chemical reaction progress. Or in other words, it's chemically frozen. And our recent work and also shows that unless the first stage ignition occurs in the unburned mixture, the flame speed of a hot flame won't change. So if it's not because of auto-ignition chemistry, then what causes is non-monotonicity in terms of flame speed of iso-octane. So we conducted 1D unsteady simulation for this problem. And where we tried 3 different ignition energies, a low ignition energy, a medium ignition energy, and high ignition energy. And also we tried 2 different data processing methods. The first method is, in order to be consistent with the experiment, is we directly average the flame speed in a radius range of 0.75 to 1.75 centimeter. The second method is more popular, is we do the interpolations in this stretch flame dynamic regime. So basically, pick the 500 low temperature case for example, you can see that regardless of the ignition energy and regardless of method 1 and method 2, all these simulations eventually doesn't show big difference. They have good consistency with the experiment. Similar things happens for the high temperature conditions, where regardless of ignition energy, regardless of method 1, method 2, you have pretty consistent results and good agreement with the experiment. The strange things occurs in the intermediate temperature range, where with a high ignition energy case, the evolution process is pretty normal. However, with a low and a medium ignition energy, you will see a sudden flame acceleration in the beginning. That leads to a huge bump in the flame speed, and which decays back to the regular stretch flame dynamics regime and merge with a regular flame structure in a while. And eventually, all these flame branches, they merge in a stretch flame dynamics regime as expected. But however, this overdriven flame segment during the flame initiation process will affect the result if you directly average the flame speed in a certain radius range. So as shown here, if you use method 1, still do the average of flame speed within the 0.75 to 1.75 centimeter using a low ignition energy, you can successfully capture the NTC, the negative temperature dependence of the flame speed. However, if you use method 1, but with a higher ignition energy case, since there is no overdriven flame, so the trend exhibit in the experiment is not captured. Right? And similar thing for this extrapolation, we can only have monotonicity in this flame speed. So next question is, what is this overdriven flame? What causes this overdriven flame? So to explain such a question, we actually selected 3 time instants along the flame evolution, before, on, and after the overdriven state, where we try to overlap the flame structure. And this flame structure is very unique. It's very interesting. As we can see that towards the unburned side, there is a mild temperature gradient, which corresponds to the faster depletion of the fuel, but at the same time, the oxygen hardly changes. That implies this is a thermal pyrolysis or thermal decomposition process, which subsequently generates a lot of C1 to C4 fragments. And this C1 to C4 fragments at a certain point, they tend to autoignite and leading to a much steeper reaction region with a much steeper temperature gradient. And this is the flame of the CO and C1 to C4 fragments, which tends to propagate faster and swallows the milder reaction zone segment controlled by fuel pyrolysis. And this flame structure, of course, is unstable because this segment propagates much faster, and eventually it will take a few moments to approach the regular flame structure. And that causes the overdriven flame. And you might ask why this overdriven flame only occurs around 750 Kelvin range, not for low temperature, not for high temperature. The reason is that at low temperature conditions, the thermal pyrolysis reaction is not that favored. Right? And at higher temperature conditions, although your fuel pyrolysis is favored, but your flame initiation is much easier and it's much faster. So therefore, there's no sufficient time allowed for this overdriven flame to occur. So more detailed results of this work is reported by our collaboration work with Professor Chen from Peking University and Professor Hansen from Stanford on this combustion flame paper. And this work basically, to summarize it, we have performed time scale and chemistry analysis to show that the observed non-monotonic behavior of high temperature iso-octane flame propagation is irrelevant to the low temperature chemical kinetics and autoignition chemistry. And we also found that in the intermediate temperature range with lower ignition energy, we can actually have a fuel pyrolysis induced overdriven flame, such an overdriven flame can well describe the negative temperature dependence of the experiment. So in the third part, I want to talk about how we can, as a combustion scientist, how we can extend the phenomena and the concepts of flame initiation to study the lithium-ion battery thermal runaway. Because in recent years, I receive more and more questions from my students. As a combustion expert, as we major in combustion, do we have a future if the future ground transportation is full electric instead of eclectic? So I told them the answer is yes, because there are lots of challenges even in the battery research, and some of the challenges requires a solution from the combustion community. So when I say challenges, actually means opportunities. I think there are at least 4 different challenges of battery research. The first one is the lithium-ion battery has a relatively low energy density. If you consider the typical energy density is about 250 watt-hour per kilogram, that is about 2 orders of magnitude lower compared with the value of gasoline and diesel, which is about 45 megajoules per kilogram. And that leads to the necessity of large size of battery packs in the vehicles, and that aggravate the slow charging problem. And that also drives the need for the exploration of new materials. The second challenge is related with a battery lifetime, because there is substantial degradation during the usage of the batteries after many cycles of charging and discharging. There can even be physical fractures within the battery. There can be local lithium plate and dendrite formed, which can actually causing dangers and hurts the battery. So the third challenge is there is a substantial need for low cobalt materials, and also there is a strong need for the green recycle methodologies for batteries after they cannot function. Okay. The fourth challenge is the battery is a thermochemical energy storage device. Of course, it's very sensitive to temperature. It has very poor power output under low temperature conditions, and under high temperature conditions, it's going to have essential danger and potential for thermal runaway. And this is a part that I think as a combustion community we can contribute. I would consider this is a combustion problem. As reviewed in this table, you can see that most of the electric vehicle or a plane accident is actually caused by internal short circuit or external short circuit of lithium-ion batteries. And such a process, what happens in such a process is basically the short circuit tends to create hotspot within a battery pack. That hotspot tends to trigger some unwanted reactions on the battery material, including the electrode and the electrolyte. Right? So as inspired by the hotspot ignition from the combustion research, I'm going to raise 2 questions. The first question is, what is the threshold condition and the kinetic feature of thermal runaway? Second question, during a typical internal short circuit scenario, what is the heat release rate? Is that going to satisfy that critical condition for thermal runaway? All right. So by drawing analogy of the hotspot ignition of flames, and we can actually build a model to describe the thermal runaway of lithium-ion batteries, and actually compare with the combustion chemical kinetics, you can see that the chemical reactions in the battery thermal runaway is still in the infant stage, where we use very global heat source terms to describe some semi-global reactions, like in 4 reactions, SEI decomposition, reactions between the anode and the electrolyte, reactions between the cathode and electrolyte, and the electrolyte decomposition reactions. And these reactions including many parameters that to be determined from TGA, DSC, or ARC experiment. So this is kind of the state-of-the-art thermal runaway reactions. And with these reactions, you can say some of the oven test in performed on lithium-ion battery can actually be pretty accurately captured. So using this model to describe thermal runaway chemistry, we can build a 3D model on this prismatic cell, where we have a cylindrical region. We add a heat source with a certain duration, Q. And outside, and then this cylindrical region is used to mimic the internal short circuit or nail penetration. And outside of this cylindrical region, we consider the battery. Inside the battery, there can be the potential of these 4 different energy source terms. And we found that there indeed exhibits a critical state. For example, starting from this heat source intensity and duration time, if we either reduce the heat source intensity from 1.18 to 1.17, the thermal runaway cannot occur. Or we reduce the duration time from 14 seconds to 13 seconds, the thermal runaway cannot occur. That means this is a critical state. It's critical state including a pair of heat source intensity and duration time that can describe the critical condition for the onset of thermal runaway. So by identifying many different pairs of this critical heat source intensity and duration time, we connect them, we can actually form a regime diagram. This regime diagram basically means for a certain duration time, if your heat source intensity is above a certain threshold value, thermal runaway is going to occur. Otherwise, it's safe. Right? So this table can basically, it's very simple, but it can give a good guidance in terms of the control of batteries. And also we have found that the thermal runaway also depends on the battery materials. We do the same thing for different battery materials and also for different radius size for that internal short circuit region. And moreover, we actually using the combustion analysis method to analyze the thermal runaway process. So the first method is we actually trace the contribution of each heat source term from that 4 reactions. And we found that if you compare these 2 cases with the same heat source intensity, but different duration time, one without thermal runaway, one with thermal runaway, you find that this negative electrode and electrolyte reactions has the strongest correlation with the thermal runaway. And also we can actually perform sensitivity analysis to understand what is the most important reaction that affects the delay time of thermal runaway. And we found that it's actually the positive electrode and electrolyte reactions. So these are all from the combustion methods. And the second question I raised is, during a typical internal short circuit, what is the heat release rate? Will that be able to satisfy the critical limit for thermal runaway that we have just identified? So we actually built up a multi-physics model by considering only 1 layer of batteries, positive electrode separator, negative electrode, and we add a piece of metal that bridging this positive electrode and negative electrode. And we can actually solve the solid phase and liquid phase, including diffusion and migration process in the electrodes. And we consider different source terms that include an energy equation. And we also imposing appropriate boundary conditions, we can actually simulate this internal short circuit scenario, where we can actually get the evolution of current, voltage, and heat release rate. And what we found is that during the typical internal short circuit, the current actually can be 1 order of magnitude higher than the 1C rate current, which is the current corresponding to the charging, full charge during 1 hour. And also we have shown that in the beginning of the internal short circuit region, the maximum heat release comes from that piece of metal. After that, the maximum heat release comes from the non-particle intercalating regions at either side of that piece of metal. And we also compare different battery materials. We found that lithium phosphate during the same condition, under the same condition, can actually have the lowest temperature rise during an internal short circuit. So that means this battery lithium phosphate has a potential to be safer. Okay. So this is a summary of the third part, is where I'm just as a useful trial to extend our knowledge and method from combustion to study the hotspot ignition in lithium-ion batteries, where we do identify the critical condition for thermal runaway. And we also using these methods like heat release rate analysis and sensitivity analysis, we can identify the key reactions, the key parameters in the models. Right. So more details of this research can be found in our recent paper in Applied Energy. And with that, I want to thank my sponsors, Department of Energy, Ford Motor Company, BASF, and Los Alamos National Lab. I want to thanks to my collaborators and our mentors and all my graduate students, undergraduate students, and high school students. So thank you for your attention. I think we have plenty of time so we can have discussions or questions. Thank you very much.
Thanks, Peng, for a very nice talk. It's pretty amazing it can cover such a broad application and motivation. Professor Zhu asked, how does the heat release in and after the cool flame depends on the stretch rate in explaining the stretch effect on cool flame speeds for lean and rich mixtures?
So basically here shows that, after a certain duration time, the cool flame actually successfully transitions to a hot flame. And this is a regime 4 of the stretched flame dynamics regime of the cool flame, where we compare the lean, stoichiometric, and rich cases. We found that all of them actually gradually, the heat release rate actually increases because of the shifted equilibrium of the low temperature kinetics. As the flame expands, your flame radius increases, stretch rate decreases, your residence time within the flame structure actually elongated. So that gives more time to facilitate the quasi-equilibrium of low temperature chemistry, gives you a stronger heat release rate. And this phenomena cannot be described by any Lewis number effect analysis from the classical stretch flame theory. It's basically a shifted equilibrium of the cause of the low temperature kinetics.
The next question is from Isaac. In the laser ignition study described in slide 15, how
Yes.
repeatable are the characteristics of the laser-induced ignition? And how repeatable are the shock characteristics and deposited energy, etc.?
Based on so many publications and from Professor Hansen group and so many consistent results, I have no doubt that the shock wave is definitely very repeatable. But there is one ambiguity in this experiment is they don't know exactly the ignition energy contained in a laser pulse. And that's the next step. They're trying to quantify the ignition energy. And for the laser, I think they can still tune the duration time of the pulse and also the wavelengths of the pulse, and this is a laminar kind of a well-controlled condition. So in turbulent ignition cases, sometimes you have a probability associated with the ignition process. But in these cases, I think the ignition is always very repeatable if your ignition energy is much higher compared with the minimum ignition energy.
So the ignition energy is not measured yet, but whether the ignition...
It's estimated. The estimated ignition energy to be less than 25 millijoules. That's why in our simulation, we tried 3 different ignition energies, a very low, like intermediate, and high ignition energy. We try to say if that can help to explain the trend observed in their experiment. In our simulation, that's estimated based on previous experience. And you can do a parametric study to say how will that further affect flame initiation process.
The next question from Jennifer Wynn, slide 13. When you refer to cool flames, is the low temperature limit, for example, would as cryogenic hydrogen flame release at 60K, but stronger according to your theory?
I don't know. I didn't try any cryogenic hydrogen flames, but we're talking about cool flames, which is the coupling of the low temperature chemistry and transport. You need to demonstrate it using a fuel that with the low temperature kinetics, or primary reference fuel for gasoline, or those fuels for diesel or for jet fuels. Under the desired conditions, they're going to have that.
I think it will be very helpful and guidance to the community if you could predict when such regimes, as you have shown for DME, would happen for just any fuel.
Right, exactly.
How much the fuel kinetics, let's say you have isobutane, or you have, propene or iso-octane or neopentene or whatever, if the, let's say, magnitude of the expected kinetics in the low temperature regime will be shown to have a significant or less significant effect. And then also how the boundary conditions of your flame and the homogeneity of your reactor would play into, size and so on into these regimes. So
right, exactly.
It would be helpful if you could give a more systematic assessment.
Yeah, yes, definitely in the future, we can extend this research to the fuels from different class with different low temperature reactivities. And we also are going to investigate the phenomenon under different thermodynamic conditions, because there is a very important time scale comparison within this conditions: flame initiation time versus the ignition delay time, right? So for the iso-octane case, for example, the ignition delay is pretty long, so you can have these overdriven kind of flames that being initiated. Didn't say a cool flame in that range. But for unhapting, as shown in the recent measurement from Professor Hansen's group and a collaboration work with Professor Zhao, and they have shown the cool flame assisted hot flame, basically a double flame, right? And also with with the fuels with different low temperature reactivity, we're going to have this phenomenon occurring at different stages, and with the inhomogeneity occurring in the actual reactors, say stratifications. I'm sure that will substantially affect the flame regimes. We have done some computational work on auto-ignition flame dynamics with the mixtures with the concentration and temperature gradient. I think many of you have done similar work, like Professor Zhou, like Professor Chen. There can be multiple different kinds of flame regimes, even including premix, non-premix, cool flame, hot flame, warm flame. They can have very complicated dynamic interactions. And I think we're still in the process of completely understand them and predict them for different situations and for different fuels.
Okay, the next question from Professor Zhu: if you truncate the low temperature chemistry, how is the pyrolysis-driven flame speed affected?
That's a great question. We actually didn't try that, but because we directly look at this and we directly simulate, there is no low temperature chemistry, although our mechanism does have low temperature chemistry, but low temperature chemistry doesn't actually manifest. I think the time scale comparison clearly explains that, because your low temperature chemistry is very unreactive. It takes 2 orders of magnitude time to show itself. That's actually a very interesting thing, because if I increase the pressure, I can make this 2 times closer. So it's possible that we can have mixed flame regimes. And if you think that thermal pyrolysis and cool flames are competing pathways, so I think there can be very interesting competitions there.
Peng, I just want to comment back that what recently we found that because of the low temperature chemistry, you have 2 oxygen or 3 oxygen addition to the molecules. Your reaction rate actually is proportional to the square or even to the cubic of the oxygen concentration. So if you get high pressure at the oxygen-rich conditions, your low temperature can compete with pyrolysis. That would be very interesting. You can work together to get a paper on that.
That's very interesting. Yes.
So Peng, how high temperature do you think you need for these two to come together at the same time scale?
I don't know. I'm trying to tune the pressure because you can say that if I increase the pressure, not only that the ignition delay time will gradually decrease, but also the NTC and low temperature chemistry will shift towards the high temperature conditions. So there is going to be, I suspect, a regime where we can have the interactions overlap between different flame regimes, where we can say more interesting phenomena, right? If you just think about from this ignition delay versus flame evolution time.
Yeah.
This is, of course, depends on the fuel, depends on the ignition energy, because a larger ignition energy, you won't say it, you will have a lower or intermediate ignition energy gives you a longer flame initiating time. And there are knobs to tune both fuel reactivity and the fuel evolution time. So there can be some very interesting phenomena, I have to suspect. And also, if you think about Professor Zhou's simulation on the double flame, I suspect under certain conditions, we can have more complete regime where we can have cool flame, overdriven, thermal pyrolysis induced overdriven flame, or the auto-ignition assisted flame. That will be even more interesting.
Okay. The next one, again from Katharina, about your battery study.
Okay.
Do you have numbers on actual thermal problems for current generation lithium batteries? What is the fraction of encountered problems?
Now you showed data up to 2016, and I was just wondering whether the known problems have been fixed. I was just interested whether the, let's say, the battery architecture has already taken care of some of the, let's say, issues that would lead to hotspots by, the electrochemistry community. That was kind of the question, and whether whether let's say the fraction has dropped with certain manipulations in the battery. That's a physical question.
So definitely, because in our modeling, the boundary condition we put is adiabatic. In the real battery electrical vehicles, you have the cooling system. And not only the cooling system will control give you a much more homogeneous temperature within the cells, but also in the case of one battery thermal runaway explosion, the coolant might help to prevent the propagation of thermal runaway among different cells. That does help a lot, but still, there can be extreme cases like your collision, penetration. The battery contains energies like a bomb, and also in our investigation, we actually didn't consider the venting gas, which is also an important issue. Is a battery thermal runaway is going to generate lots of hydrocarbon like methane, ethylene, and those fuels, those gaseous fuels, are going to generate flame and help to spread the fire. So you have the coolant, which is good, but also in the real scenario, you have the jet flame generated from the battery, and the real scenario is going to be really complicated. And that also depends on the battery material, what electrode, what kind of electrolyte you are using. And you will have different gases. And what is the state of charge of your battery? That's also going to affect the gases that you can generate. I think there's lots of exciting things that we can work in that area.
Okay, the next question from Zhao. How is the source term of chemistry considered in your modeling, especially around the cathode? Which reaction are most corresponding to the heat race?
So the source term, we basically use a very simple source term. Is a constant source term that lasts for a few seconds, lasts for the certain duration time. And we're going to use very fine grids to resolve the interface, because that's a part you might have the highest temperature and the triggers reactions. So from the triggering of the thermal runaway reactions, you can say that SEI decomposition occurs first. Once the SEI is decomposed, then you can have the direct contact of electrode and electrolyte that triggers the subsequent reactions. that's kind of my understanding based on this simple model.
And next one from Wang Han. So he has a question regarding minimum ignition energy of cool flame initiation.
Okay.
So he said, as you know, Professor Law's group found that at certain conditions, turbulence can facilitate forced ignition of mixture with a large Lewis number. Can you give some comments on turbulence effect on cool flame initiation by hotspot?
That's a great question. I haven't done things on that part, but I would suspect that really depends on your turbulent intensity. And turbulent cool flames, I guess Professor Michael Mueller and one student is working on that. You might check. That's kind of the only work I know about turbulent cool flames. But other than that, I didn't see much work in that field, probably because of cool flame. Once you have fluctuations, disturbance from the turbulence, it might break the cool flame structure. That of course depends on your turbulent combustion regime. But I have to say that is a primary reason why we haven't seen much work in that field.
Kaoru Maruta, regarding battery analysis, will there be similar behaviors expected in DMC and DEC?
That's a carbonate
and diisocarbonate.
The electrolyte really matters for thermal runaway. You want to control the reaction between the electrolyte and the electrode of the thermal runaway. Also, the electrolyte itself can decompose and releasing different gases. And that's also the majority, one of the major reasons that people are talking about solid state batteries, because solid state battery perhaps won't have such problem.
Yeah, I think that the similarity with DME is the oxygen in the fuel. So probably that my question should be converted into something like that, any effect of the small difference in the low temperature chemistry of the fuel. Such small difference affects on the results of the analysis.
I'm sure it will quantitatively affect results, but for the method and concept, it won't.
So that's all the question we have. Let's thank our speaker again in whatever way you want.
Everybody turn on your camera and try to thank Peng and breathing combustion to battery, which generate impact on other areas. I like to make a announcement also that there is a fifth chemistry workshop organized by Niels Hansen and on between November 30 to December 1st. Every day it's about 2 hours to discuss all these chemistry issues from elementary chemistry all the way to supercritical and conditions. Welcome to join us. And you can find the information on my website and contact Niels Hansen.